Atomic Linux is one of those ideas that sounds small at first, just a different way to update your system. But once you understand it, you realize it completely changes how Linux can work on the desktop, on servers, and even in the cloud. For decades, traditional Linux distributions have followed a familiar model: install the system, use a package manager, update packages individually, modify configuration files directly, and hope nothing breaks during a major upgrade. It has worked remarkably well, but it also comes with fragility. A single broken dependency, a partially completed upgrade, or a conflicting configuration change can leave a system unstable. Atomic Linux proposes a fundamentally different approach. Treat the operating system as a single immutable unit that updates atomically, all at once, with the ability to roll back instantly if something goes wrong. To understand Atomic Linux, we first need to understand what atomic means in this context. In computing, an atomic operation is one that is indivisible. It either completes entirely or does not happen at all. There is no halfway state. Applied to operating systems, this means that when you update the system, you don't update hundreds or thousands of individual packages one by one. Instead, you switch from one complete system image to another. If the update succeeds, you boot into the new image. If something fails, you remain on the previous one. There's no broken in-between state. Traditional Linux systems rely on package managers like apt, dnf, or pacman. These tools download and install packages individually, resolving dependencies dynamically. During updates, packages are replaced in place. If power is lost or a dependency conflict arises, you can be left with mismatched versions. Over time, configuration drift accumulates. Systems that started identical gradually become unique snowflakes. Atomic Linux solves this by separating the core operating system from user modifications and treating the base OS as read-only. One of the most prominent examples of Atomic Linux is Fedora Silverblue, which is built on the Fedora ecosystem. Fedora Silverblue uses a technology called rpm-ostree. Instead of installing packages directly into the live root file system, rpm-ostree composes a complete file system tree from RPM packages into a single image. That image becomes the base OS. When you update, you download a new image and deploy it alongside the old one. On reboot, the system switches to the new deployment. The previous one remains available for rollback. This means updates are transactional. They either fully apply or not at all. What makes Fedora Silverblue particularly interesting is how it changes the user workflow. Since the root file system is read-only, you don't install applications the traditional way. Instead, user applications are typically installed via Flatpak. Flatpak is a containerized application distribution system that isolates apps from the base OS. Separation reinforces stability. The base OS remains clean and consistent, while applications live in their own sandboxed environments. For development tools or custom software that needs deeper system integration, you can use Toolbox, which creates a mutable container environment where you can install packages with DNF, as if you were on a traditional system, without modifying the immutable base. The idea of immutability might sound restrictive, but in practice it creates freedom. When the base system cannot be casually altered, it becomes predictable. You always know what the underlying OS looks like. Debugging becomes easier because there is less hidden state. Reproducibility improves dramatically. This is especially powerful in enterprise environments where fleets of machines need to remain consistent. Another major player in the Atomic Linux world is openSUSE MicroOS. MicroOS applies similar principles, but with a different technological stack. Instead of rpm-ostree, MicroOS uses transactional updates built on Btrfs snapshots. Btrfs is a modern Linux file system that supports copy-on-write snapshots. When MicroOS performs an update, it creates a new snapshot of the root file system. Changes are applied to that snapshot, not the currently running system. On reboot, the system switches to the new snapshot. If something goes wrong, you can boot into a previous snapshot. The atomicity comes from the snapshot mechanism, rather than an image-based composition model. MicroOS is used as the foundation for openSUSE Eon, which targets desktop users, and openSUSE Culpa, which focuses on KDE Plasma. In the server space, SUSE leverages similar ideas in its container-focused and edge-oriented offerings. The emphasis is the same: minimize mutable state, maximize reliability. Beyond Fedora and openSUSE, the atomic concept has influenced many other projects. Ubuntu has Ubuntu Core, which is designed primarily for IoT and embedded devices. Ubuntu Core uses snap packages and a read-only base system. Updates are transactional and rollbacks are supported. The entire system is constructed from snaps, including the kernel. This design makes it highly resilient and suitable for unattended devices deployed in the field. Even outside traditional distributions, the atomic philosophy is deeply embedded in container-native operating systems. Take Fedora CoreOS as an example. Fedora CoreOS is designed for running containers at scale. It uses rpm-ostree and automatic updates. It is meant to be mostly invisible. You don't SSH in and install packages manually. You define the system configuration declaratively using tools like Ignition, and the system converges to that state. This approach is extremely powerful in Kubernetes environments. The atomic model aligns closely with the broader shift in computing toward declarative infrastructure. Instead of manually changing systems, you describe the desired state. The system enforces that state. If something deviates, it can be reset or re-provisioned. Atomic Linux distributions are naturally compatible with this philosophy because their base state is tightly controlled. One of the strongest arguments for Atomic Linux on the desktop is stability. Many Linux users have experienced the anxiety of a major system upgrade. Will the new version break drivers? Will configuration files be overwritten? Will the desktop environment behave differently? Atomic systems reduce this risk because upgrades are image-based. If the new version fails, you simply reboot into the previous deployment. There's no need to repair a half-upgraded system. Security is another major benefit. Because the root file system is read-only, malware has a harder time embedding itself deeply into the system. System files cannot be modified casually. Combined with application sandboxing through Flatpak or Snap, this creates multiple layers of defense. Atomic updates also ensure that security patches are applied consistently and completely. However, Atomic Linux is not without trade-offs. The most obvious is flexibility. Traditional Linux allows you to modify nearly anything. Want to replace a core system library? Go ahead. Want to experiment with a custom kernel build directly on your main system? No problem. Atomic systems discourage this kind of deep mutation. While you can layer packages on top of rpm-ostree and Fedora Silverblue, each layer creates a new deployment and increases complexity. The intended workflow pushes users toward containers and user space isolation instead of modifying the base. There is also a learning curve. Users accustomed to DNF or apt may initially find the new workflow confusing. Installing a graphical application via Flatpak instead of the system package manager feels different. Using toolbox containers for development instead of installing compilers directly into the OS requires a mindset shift. But once understood, many users find it cleaner. Performance considerations are sometimes raised. Image-based updates can be larger than incremental package updates. However, technologies like Delta updates and content addressable storage reduce redundancy. In many cases, the difference is negligible, especially given modern bandwidth availability. Another interesting aspect of Atomic Linux is reproducibility. Because the base OS is built from a defined set of packages into a single image, you can reproduce that image consistently across machines. This is extremely useful in enterprise deployments. It also aligns with the rise of GitOps methodologies, where infrastructure definitions are stored in version control and systems are rebuilt rather than manually repaired. The atomic concept also intersects with the idea of immutable infrastructure in cloud environments. In traditional server management, administrators log into machines and apply patches manually. Over time, each server diverges slightly. In immutable infrastructure, servers are replaced rather than modified. You build a new image, deploy it, and decommission the old one. Atomic Linux distributions bring this philosophy directly into the OS design itself. One subtle but powerful benefit of Atomic Linux is mental simplicity. When users know that the core system is stable and protected, they can experiment more freely at the application level. If something breaks inside a container or Flatpak sandbox, it does not corrupt the base OS. The boundary between system and application becomes clearer. Fedora's Atomic offerings have evolved significantly over time. What began as Project Atomic expanded into Silverblue for desktops, Kenoid for KDE, Sarisia for Sway, and CoreOS for containers. The common thread is rpm-ostree and image-based updates. Each variant targets a slightly different audience but shares the same underlying principle. The OS is a managed image, not a mutable collection of packages. openSUSE's approach emphasizes the power of Btrfs and Snapper. The snapshot system allows fine-grained rollbacks, not just for full system updates but also for configuration changes. This gives users confidence to experiment, knowing they can revert to a known good state. Looking forward, Atomic Linux may represent the future of mainstream Linux distributions. As Linux adoption grows among less technical users, the tolerance for system breakage decreases. People expect their computers to update reliably like smartphones. They do not want to resolve dependency conflicts or manually merge configuration files. Atomic updates provide a path toward that user experience without sacrificing the power and openness of Linux. At the same time, power users still need flexibility. The challenge for Atomic distributions is to balance immutability with customization. Technologies like layering, containers, and declarative configuration aim to provide that balance. Rather than modifying the system directly, users define overlays or container environments that extend it. The rise of Flatpak is closely tied to Atomic Linux. By decoupling applications from the base OS, Flatpak reduces compatibility issues. Developers can target a stable runtime instead of worrying about every distribution's package versions. For Atomic desktops, this is essential because it avoids breaking the read-only base. Another fascinating dimension is how Atomic Linux simplifies recovery. If a traditional Linux system fails to boot after an update, recovery may require crude environments, manual package fixes, or even reinstalling. In Atomic systems, you simply select the previous deployment from the bootloader. Recovery is built into the design. Edge computing and IoT are also major beneficiaries. Devices deployed remotely need reliable, unattended updates. Atomic systems can download updates in the background, switch deployments on reboot, and roll back automatically if health checks fail. This dramatically reduces maintenance costs. Despite its advantages, Atomic Linux will not completely replace traditional distributions overnight. There will always be environments where full mutability is necessary or preferred. Developers working on low-level system components may need direct access. Experimental users may prefer total control. The ecosystem will likely remain diverse. But the direction is clear. As computing moves toward containers, cloud-native architectures, and declarative management, the operating system itself is becoming more appliance-like. Atomic Linux embodies this shift. It treats the OS as a stable foundation, not a playground for constant mutation. In practical terms, adopting Atomic Linux means changing habits. You think in terms of images and deployments. You separate system and application. You rely on rollbacks instead of repair. You accept that the base is not meant to be endlessly tweaked. And yet the irony is that this constraint often results in greater long-term flexibility. A stable foundation enables more experimentation above it. When you trust that your system can recover instantly, you are less afraid to update, to test, to explore. Atomic Linux is not just about technology. It is about philosophy. It asks a fundamental question. Should the operating system be something you constantly modify or something you trust and build upon? Fedora, MicroOS, Ubuntu Core, and others have chosen the latter path. As hardware becomes more powerful and storage cheaper, the cost of image-based updates becomes less significant. The benefits of reliability, security, and reproducibility become more compelling. Atomic Linux may well become the default expectation rather than the alternative. In the end, Atomic Linux represents maturity. It acknowledges that while Linux has always been powerful, it can also be fragile when mismanaged. By making updates atomic, systems immutable, and rollbacks effortless, it reduces that fragility. It brings Linux closer to the reliability users expect from modern computing platforms, while preserving the openness that defines it. Whether you are a developer, a sysadmin, or a curious desktop user, understanding Atomic Linux is increasingly important. It is not just another distribution variant. It is a rethinking of how operating systems should evolve in an era defined by containers, cloud-native workloads, and continuous delivery. The Atomic model may not be perfect, and it may not suit every use case. But it is one of the most significant shifts in Linux design in recent years. Fedora Silverblue, openSUSE MicroOS, Ubuntu Core, and similar projects are not experiments on the fringes. They are signals of where Linux is heading. Atomic Linux is about confidence. Confidence that updates will not break your system. confidence that you can roll back instantly. Confidence that your base OS is consistent and secure. In a world where computing infrastructure grows more complex every year, that confidence is invaluable.